The second illustration we are looking at is an illustration in R3. So here we have three equations, three unknowns. So I want you to consider the following system. We have 2x sub 1 minus x sub 2 equals 0. That's equation 1, or row 1. We then have minus x sub 1 plus 2x sub 2 minus x sub 3 equals negative 1 for equation 2. And equation 3 is minus x sub 2 plus 4x sub 3 equals 4. So the first thing that I want to do here is simply break down the system. Let's think about the three equivalent formats that we are familiarizing ourselves with. So the first form is the matrix equation. So the matrix equation we know now has the form A times vector x equals vector b. So looking up at our system, we can see the coefficient matrix. And if it helps, you can even add little zeros where we have those empty spaces. So let's see, the first column of our matrix is 2, negative 1, 0. The second column is negative 1, 2, minus 3. And our third column is 0, negative 1, 4. And now we are multiplying this matrix A, this coefficient matrix, by vector x in R3. So it has three entries, x sub 1, x sub 2, x sub 3. And this is equal to the constant vector, vector b, defined by the components 0, negative 1, 4. So there you have it. That's the equivalent matrix equation. Now we can also write this in the equivalent vector equation. So again, since we have a vector x in R3, we could write this as x sub 1 times the first column vector, a sub 1, plus x sub 2 times the second column vector, a sub 2, plus x sub 3 multiplied by that third column vector, a sub 3, and that is equal to vector b. And again, these vectors a sub 1, a sub 2, and a sub 3 are the column vectors of the matrix A. So here we go, breaking this system down to its vector equation form. We have x sub 1 multiplied by the first column vector, 2, negative 1, 0, plus that second scalar, x sub 2, multiplied by the second column vector, negative 1, 2, minus 3, plus our third scalar, or our third weight, x sub 3, multiplied by the third column vector, 0, negative 1, 4. And that linear combination of the column vectors is equal to the constant vector, 0, negative 1, 4. And last but not least, we can also rewrite this system in the equivalent augmented matrix. And again, the augmented matrix is the form that we will solve our systems in. So our augmented matrix here, we have three column vectors, a sub 1, a sub 2, a sub 3. There's your coefficient matrix. And we augment this with vector b. So here, our augmented matrix for the system is 2, negative 1, 0, negative 1, 2, minus 3, 0, negative 1, 4. And we augment this with the constant vector 0, negative 1, 4. And there you have it. We have our four equivalent formats. Again, we have the system of linear equations that's given. We have rewritten this as the matrix equation, the vector equation, and the augmented matrix. So let's now take this one step further and think about the geometric interpretations of both the row picture of this system and the column picture of this system. So here we go. We are considering the row picture. So again, to see that row picture, we want to literally look across each row, one at a time. Now, I want you to note that since we're in R3, what are the graphs of each row? So since we are in R3, the graph of each row is a plane. Yuck. So While planes are fine, sketching a graph of each plane is going to be tricksy work, right? So the goal that I want you to keep in mind of the row picture is to find a point that satisfies each plane. So to find a point or ordered triplet, x sub 1, x sub 2, x sub 3, that satisfies each plane. So it's going to be, once you get past R2, it's going to be a little bit tricky to find the row picture. Because in theory, we are looking for, we'll say this is our first row, the plane of row 1. And then we've got another plane, let's say over here. Here's our second plane, that's the row 2 picture, R2. And now in addition to this, we have a third plane. Now we'll say over here. Here's our third plane. Now, our job with the row picture is to find the point that satisfies each one of these. Right there. So it's going to be tricky to sketch a row picture above R2. So we have a good enough interpretation of what we're looking for in the row picture here. It's going to be much easier and more satisfying to consider the column picture when we're working with a linear system in R3. So here we go, the column picture of our linear system. So just like we saw with the illustration in R2, when you're thinking about the column picture of a linear system, you want to start by thinking about the vector equation. So here our vector equation is x sub 1 multiplied by the first column vector 2, negative 1, 0, plus x sub 2 multiplied by the second column vector, negative 1, 2, minus 3, plus our third column vector, we have plus x sub 3 multiplied by the third column vector, 0, negative 1, 4, and this is equal to the constant vector 0, negative 1, 4. So perhaps you're picking up on the solution to the system already. So before, I want you to again keep in mind that the column picture asks us to find the correct combination of the columns of matrix A that are going to produce vector B. So put in more simple terms, we want to write this vector B, that constant vector, as a linear combination of the columns vectors A sub 1, vector A sub 2, and vector A sub 3. So this example is easy enough that we can actually see the correct combination. Do you see it? If you don't, have no fear. Normally we would solve this algebraically by row reducing the augmented matrix, but this example was selected because we can pretty easily see the correct combination. So looking up again at our vector picture here, did you notice that column vector A sub 3 matches the constant vector B? So what is this telling us? Well, this is telling us that we're going to need none or 0 of column vector A sub 1. This tells us that we're going to need 0 of column vector A sub 2. This lets us know that we're going to need just 1 of column vector A sub 3. This is the correct linear combination of these 3 column vectors to produce that constant vector B. We're going to do none of the first column plus none of the second column plus 1 of the third column to produce vector B. So these coefficients, these scalars or these weights, are again letting us know the solution to our system. Right, this is the intersection of those 3 planes. The column vector x sub 1, x sub 2, x sub 3 is 0, 0, 1. So a unit vector in the x sub 3 direction. So let's again think about this geometrically. So to think about this geometrically, we want to begin by sketching each column vector. So again, we have column vector A sub 1. So I'm going to approximate here. Again, if you have graphing paper, this is going to be a good time to use it. So from the origin, we need to move 2 units in the x direction. We then need to move 1 unit in the negative x sub 2 or negative y direction. So here is your first column vector. This is column vector A sub 1, defined by the components 2, negative 1, 0. Our second column vector, vector A sub 2, again, we start from the origin, and this time we are going to move 1 unit in the negative x sub 1 direction. We'll move 2 units in the positive y direction, and then we need to move 1, 2, 3 units down in the x sub 3 direction, or the z direction. So here is our second column vector, vector A sub 2, again defined by the components negative 1, 2, negative 3. And last but not least, we need vector A sub 3. So again, we're starting at the origin. We're not moving in the x sub 1 direction. We're going to move 1 unit in the y direction, in the negative y direction, and then 1, 2, 3, 4 units up in the x sub 3, or the z direction. So here is our third column vector, vector A sub 3, defined by the components 0, negative 1, 4. And now to sketch the column picture, we need no scalar multiples of our first column vector. We need no scalar multiples of the second column vector, so we're still here at the origin. And then we need 1 scalar multiple of A sub 3. So and there it is. This is the same vector. It's also equal to our solution vector, vector B. So here is the geometric interpretation of our column picture in this case. And we have here produced the correct combination of the columns of matrix A that are going to produce that constant vector B, or the vector on the right-hand side of your equal sign. Now, this example is all well and good, but what about if we spice it up a little bit? So here we go, we're living on the edge. Let's consider an extension of the previous illustration in R3. But this time, let's go ahead and suppose that vector B is now the vector 1, 1, negative 3. So the only part of the matrix equation that changes is the constant vector. We still have the same coefficient matrix, matrix A, times this unknown vector x in R3, and this is equal to the new vector B. So I want to consider the column picture of this new linear system. So again, let's keep in mind, what is the goal of our column picture? Well, the goal is to write this new vector B as the correct linear combination of the columns of matrix A. So the column vector is vector A sub 1, vector A sub 2, and vector A sub 3. So let's take this system and write it in the equivalent vector equation form. So we have x sub 1 times our first column vector, 2, negative 1, 0, plus the scalar x sub 2 multiplied by the second column vector, negative 1, 2, negative 3, plus that third scalar, or the weight or coefficient, multiplied by the third column vector, 0, negative 1, 4. So that linear combination is still the same thus far, but now this is equal to the constant vector B, 1, 1, negative 3. So our job is to determine the values of x sub 1, x sub 2, and x sub 3. We need that correct linear combination of these 3 column vectors of our matrix that are going to produce the new constant vector B. So, can you see it? Can you see that correct linear combination? Again, if you can't, have no fear. Normally, we would take this matrix equation and we would convert it to the equivalent augmented matrix and use row reduction to find the exact solution algebraically. But this is another example where if you take a moment, pause for a cause, literally pause the video, see if you can see the correct combination. Have you found it? So my hint is, what happens when you add the first column vector to the second column vector? We get vector B! Woohoo! So we can see that if we take one of the first column vector and add this to one of the second column vector and add this to none or 0 of your third column vector, we're going to produce the desired vector B. So this is giving us that correct linear combination. We're going to take one scalar multiple of vector A sub 1 and add it to one scalar multiple of vector A sub 2 and add this to no scalar multiples of vector A sub 3. So this is the linear combination of those column vectors that we need. This is also letting us know what our solution vector is here. Vector x in R3, so it has the components x sub 1, x sub 2, x sub 3, is defined specifically in this case as 1, 1, 0. So we have a different combination to produce the different vector B. So let's now go ahead and think about this column picture geometrically. So here we go. Here is space. We have the x sub 1, x sub 2, x sub 3 axes. And I've already gone ahead and plotted the 3 column vectors of our matrix because we just looked at them in the last example. So to sketch the column vector, or the column picture, we want to think about this vector arithmetic. So we need to add vector A sub 2 to the terminal point of vector A sub 1. So in other words, we're starting from the origin. Here is 1 of vector A sub 1. So you can say that's 1 times vector A sub 1. So now, in order to add that one scalar multiple of vector A sub 2 from this terminal point here, we're going to apply the parallelogram rule. So this is our parallelogram rule for vector arithmetic. So from this terminal point, we can draw the parallelogram. So here is a vector that is parallel to vector A sub 2, conveniently exactly what we're looking for. But just so you can see that full parallelogram from this terminal point, we can also see the vector parallel to vector A. And so these vectors are also parallel. So using this parallelogram, we can see the sum of vector A sub 1 plus vector A sub 2 by plotting the vector along the main diagonal of the parallelogram. So this new vector here, that's vector B, defined by the components 1, 1, negative 3. And that's exactly what we wanted. We wanted 1 of vector A sub 1 plus 1 of vector A sub 2 to produce vector B. Woohoo! So this is the column picture for this system of linear equations with our new vector B here. And I think that this example begs the question, does this work for every vector B? Could we sit here for the rest of our lives as Professor Y gives us different vector B's, and we'll be able to use these 3 column vectors to find a linear combination to produce that vector? Can we always find the column picture for every vector B? And for this example, the answer is yes. For every vector B, we can always find a linear combination of these 3 column vectors to produce that vector B. Now keep in mind that this won't always work, but it does work in this example. For every vector B in space, we will always be able to find a linear combination of the columns of matrix A to produce that vector B. Now formally, what this question is asking or saying is, do the columns of matrix A span 3 dimensions? So when we say, do the vectors span 3 dimensions or span space, we mean, do these 3 column vectors fill up space? Can we always produce a linear combination of them to find any vector or any point that we want in space? So the span is the collection of all possible linear combinations of the set of vectors you're considering. So let's go ahead and explore span in more detail.